Hello, Math 1341 Calculus 1 students. This is the first part of our review for Test 1. We will go over this sample Test 1. Please understand my caution. You will see different problems on our test. And don't only study this. There are more review materials in Canvas, but it's great practice for us. And so we will get started with number 1. We have an average rate of change and instantaneous rate of change question. Well, we want the average rate of change for f of x is 2 over x squared from x equals 1 to x equals 4. This is change in f divided by change in x. And going from 1 to 4, this would be f of 4 minus f of 1, and then divided by 4 minus 1. Now, what we can do, if it helps, we can come to the side, calculate f of 4. You see, this is 2 divided by 4 squared, which is 16. So this gives us 1 divided by 8. And f of 1, this is 2 divided by 1, which is 2. Okay, now let's jump back into this quotient. We have 1 over 8 minus 2 divided by 3. We don't leave our answer like this. We need to write this as a simplified fraction. So you notice in my numerator, this is 1 over 8 minus 16 over 8. My denominator I can also write as a fraction. It's 3 divided by 1. This allows me to invert and multiply. So I have minus 15 over 8 times 1 over 3. Here we have our final answer, negative 5 over 8. Negative 5 over 8. This is 1A. 1B, this is instantaneous rate of change. So we cannot use any rules for derivatives here. We absolutely must use the limit definition of the derivative. Using rules and evaluating will not give us any points on a question like this. So what is the instantaneous rate of change? Well, f prime of 1, it's a limit. As h approaches 0, we have f of 1 plus h minus f of 1 divided by h. The way I typically do this is I will start with just the numerator. So f of 1 plus h minus f of 1. Now, I want to simplify this until I have this as h times something. That way I can divide by h and I will not be, I will have an expression defined at h equals 0. So f of 1 plus h is 2 over, well, we put 1 plus h in for the x, so 2 over 1 plus h squared. And we already calculated f of 1. This was just 2. Maybe I'll write it as 2 over 1. Well, the strategy is get a common denominator, which in this case, the common denominator is 1 plus h squared. So I multiply this second term by 1 plus h squared divided by 1 plus h squared. Now let's see what I have. My denominator, I'll just leave alone, 1 plus h squared. Then I have 2 minus 2, 1 plus h squared. Okay, we keep going. So how am I going to get this expression here as h times something? Well, I have this squared. I'm going to need to multiply everything out. So maybe I'll write this above. You see, this is 1 plus h times 1 plus h. It is not just 1 squared plus h squared. It doesn't work like this. We need to multiply first, outer, inner, last, like this. So my next step, we have 2 minus, we have 2. This will be 1. We have a plus 2h, and then plus h squared. We're almost there. All over 1 plus h squared. Now, recopy my denominator. I'm really just working with this numerator here. We have 2 minus 2, okay, adds to 0. And what I'm left with is minus 4h, and then minus 2h squared, which we see is h times something. Hooray! We have this as h times, well, when we factor out the h, it's minus 4 minus 2h. And then I will just recopy the denominator. So, next bullet. We want f of 1 plus h minus f of 1 divided by h. So f of 1 plus h minus f of 1 divided by h. And all that happens, you see, we can copy and paste, is h over h is 1. So when we copy, it's this. Except I don't need these parentheses. This is it. This is f of 1 plus h minus f of 1 over h. The beautiful thing is this is now defined at h equals 0. And so all we need here is a limit as h approaches 0 of this. Once again, I will copy and paste. And you see what we get here. We can evaluate h equals 0. We have minus 4 over 1 squared, which is just negative 4. This one was a wonderful problem, but I also understand that this is not an easy thing to do. So this was number 1 on this sample test. Number 2, we are given a degree 3 polynomial. We want to find critical points, intervals of increasing, decreasing, classify critical points. We will also deal with concavity here. So let's get started. To find the critical points of this function, we need to find places in the domain where the first derivative is 0 or does not exist. The domain of this function is minus infinity to infinity. But let's differentiate. This is power rule. We have minus 6x squared. We have plus 6x plus 36. Now, factor out what's common to every single term. So let's factor out a negative 6. We have x squared minus x minus 6. Now we can factor this. We have minus 6. We need two numbers that multiply to negative 6 and add to negative 1. Let's take minus 3 and plus 2. Now check. We multiply these two numbers, we get negative 6. We add them, and we get negative 1. Wonderful. So f prime of x equals 0. This happens, well, when x is 3 and negative 2. We have 3 and negative 2. Now we want open intervals where the function is increasing and decreasing. The next step here is we divide the domain, which is minus infinity to infinity, into open intervals based on the critical points. So we have minus 2 and 3. And we can write our open intervals underneath. This one goes 3 to infinity. This one goes minus 2 to 3. And this one goes minus infinity to minus 2. Then we pick a point in each interval. I'm interested in the sign of the derivative on each open interval. So let's pick 0. That's an easy one to pick. Typically, it's very wonderful to evaluate things at 0. And let's pick 4. And let's pick negative 3. Okay, then I will typically make a chart where I have these 3x values that I'm going to test. And I will write my derivative factored. So minus 6, x minus 3, and x plus 2. I'm interested in the sign of the derivative. It's perfectly fine to pick different x values than me. You will get a different value of the derivative, but the sign will be the same. Okay, so minus 3, 0, and 4. So you notice this minus 6 is always negative. I'll go ahead and just write that. Now, minus 3 is negative. Minus 3 plus 2 is negative. 3 negatives makes a negative. 0 minus 3 is negative. 0 plus 2 is positive. 2 negatives makes a plus. 4 minus 3 is positive, and 4 plus 2 is positive. 1 negative makes a negative. So my first derivative goes like this. Minus, plus, minus. Now we can write our answer. My function is increasing everywhere we see a plus, which is one open interval, minus 2 to 3. And it's decreasing everywhere we see a minus, which is two open intervals, and we separate them by a comma. Minus infinity to minus 2, and 3 to infinity. Now, use this. We want to classify each critical point as corresponding to local max, local min, or neither. So I will typically just redraw my number line right around each critical point. So my two critical points are -2 and 3. And for -2, it went minus, plus. For 3, it went plus, minus. Then we just sketch. What does a function look like that does this? So decreases, increases, like this. You see, we have a local min at x equals -2. Now, for 3, we'll have some function that increases and then decreases like this. You see, local max. Local max at x equals 3. Now, the next part is about concavity. Concavity has to do with the second derivative. So I need the first derivative. Let's just copy and paste it because it's part of calculating the second derivative. Okay, here's the first derivative. I will make it a different color. Now, what I need for this question is the second derivative. So let's differentiate again. The second derivative, we have minus 12x plus 6. And the second derivative is 0. Well, when 12x equals 6, or x is 1/2. Okay, now we go about very similar to increasing, decreasing, and dividing the domain into intervals. The only difference is we're working with the second derivative and not the first. So we divide the domain, which is all real numbers, into open intervals based on where the second derivative is 0 or does not exist, which is just this one x value. And once again, I can write my open intervals underneath. It goes minus infinity to 1/2, and then 1/2 to infinity. Well, we can test. So let's pick here, we can pick x equals 0. And here we could pick x equals 1. The second derivative at 0, well, you notice this is 6, which is positive. The second derivative at 1 is minus 12 plus 6, minus 6, which is negative. So I want to put a plus here and a minus here. And now I can make my final observation about open intervals of concave up and down. This function is concave up from minus infinity to 1/2. Concave down from 1/2 to infinity. Now, we are not asked this, but if we were, you notice that x equals 1/2 is in fact an inflection point because the function switches from concave up to concave down at x equals 1/2. Okay, let's move forward. Next question is a question about limits. We have one function, which is given here. We want to calculate the limit as x goes to infinity, and we want to calculate the limit as x approaches 1. And then we have a question about continuity. First of all, let's do the limit at infinity. If we want a limit as x approaches infinity of this function, what we want to do here, because you notice what's happening, we can think about this. The numerator is going to negative infinity, the denominator is going to positive infinity, and this is an indeterminate form. So we can't just think about what's happening as x grows without bound. What we need to do is divide every single term by x to the highest power that we see. In this case, it's x cubed. So we will have 3x squared over x cubed. We have minus 3x cubed over x cubed. Then we divide every power in the denominator, or every term in the denominator, by x cubed. We have x cubed over x cubed. And then minus x over x cubed. Okay. We can simplify each one of these. So we have a limit as x goes to infinity. This one is 3 over x. We have minus 3. And then in the denominator, we have 1 minus 1 over x squared. 1 minus 1 over x squared. Okay, we're in wonderful shape. This one and this one, 3 over x. As x grows without bound, this goes to 0. 1 over x squared. As x grows without bound, this also goes to 0. So you see the limit here, it's -3 divided by 1, and I can write my answer, -3. Now, what happens at x equals 1 if we try to evaluate? You notice we get 3 minus 3 over 1 minus 1. So trying to evaluate, we get 0 over 0. And this also is indeterminate. It does not mean the limit exists. It does not mean the limit does not exist. It means we need to do something. Well, let me do some factoring right here. My numerator is 3x squared, and then I have 1 minus x. My denominator, I have an x, and then I have x squared minus 1. Okay, so you notice this is just 3x, and then we have 1 minus x, and then we have x minus 1 and x plus 1. Now, maybe one more, because what I want to do here, the issue with this 0 over 0 is the 1 minus x, or in the denominator is written x minus 1. So let's factor out a minus sign. So this is minus 3x, x minus 1. And then I have this. Okay, now we want to limit as x approaches 1. Maybe I will just put this here, cut, and paste. So this part here and here we can cancel off, and we have a limit as x approaches 1 of minus 3x divided by x plus 1. Now evaluate. This is now defined at x equals 1. We just get -3 over 2. Both of these limits exist, even though we have these indeterminate forms. So these are great questions. Let's move on. Next question, is f of x continuous at x equals 1? Well, definitely not. Why? Well, the answer is no. Because we need the limit to exist. The limit exists at x equals 1. We need 1 to be in the domain of the function. This is where we run into issues, because you see 1 is not in the domain of this function. So f of 1, I'll write it that way, 1 is not in the domain of this function. Or in other words, f of 1 is undefined. And because of this reason, the function is not continuous at x equals 1. Okay, great question. Let's move on. We have two parts to this number 4, differentiate each function, and we do not simplify. It's really a test of, can we remember our rules here? So there are a few ways we can go about g of y. Maybe I'll rewrite this as a power. So we have e to the 5y over y cubed plus 7. The power here is 1 over 5. So I'm going to do chain rule followed by a quotient rule. There's other things you could do, but this is the way I will go about this problem. So the chain rule, we would have 1 over 5, the minus 4 over 5. Okay, that was derivative of the outside. Now, we put in the entire inside function. So let's do this. Put in the entire inside function here. Then multiply by the derivative of the inside function. And this one is quotient rule. We see one function divided by another. So we have denominator times the derivative of the numerator. Don't forget the derivative of the numerator in itself is a little chain rule, because e to the 5y, when you take the derivative, would be e to the 5y times 5, which is the derivative of the inside function. So far I have denominator, derivative of the numerator, minus the numerator, and then times derivative of the denominator, and then all over denominator squared. And this is how we leave it, like this. If you want, you can put parentheses here and here. This is my answer, unsimplified. This is what it's asked for. The one thing though, absolutely do not cancel this with one of these. Simplifying fractions doesn't work like that because we have a difference in the numerator. So just leave it, don't simplify, and move on to the next question. Okay, it's another one. Take the derivative and we don't worry about simplifying. Well, I'm going to take an initial step to make my life easier here. And the first term, you see e to the ln. E to the ln of something. Well, you notice this first term is just 2x minus x cubed. It uses the fact that e to the x and natural log x are inverse functions. And then the second term I can write as a power. We have 3, 2x to the 5th plus 1 to the negative 1/3 power. Okay, well, take the derivative. We have 2 minus 3x squared. Now we bring down the power. 3 times negative 1/3 is negative 1. And then power minus 1 is minus 4/3. And we put in the entire inside function. Okay, let's do it. This is chain rule. Copy and paste. Okay, there's derivative of the outside, evaluated at the inside. Then we multiply by the derivative of the inside function, which is 10 x to the 4th. So this is this letter B. Now let's move on. Number 5. This is an inverse function theorem question. So we are considering the function 2x squared plus ln x for x bigger than 0. First, find the derivative. Well, okay, this is 4x plus 1 over x. Now we want to find f inverse of 2, justify our answer. We have to kind of look at the function here. We notice that, observe that f of 1, this is 2 times 1 squared plus ln 1. ln 1 is 0, so this is 2. Okay, so let me underline this. F of 1 is 2. This means f inverse of 2 equals 1. So that was my justification. This is the relationship between a function and its inverse. Okay, next part. Find f inverse prime of 2. Here's the inverse function theorem. It's 1 over f prime of f inverse of 2. And we have lots of steps already above. So this would be 1 over f inverse of 2 is 1. So this would be f prime of 1. And sometimes I'll make this a different color so it's a little bit easier to look at. Okay, we have everything. We have f prime. We want to evaluate f prime of 1 and take 1 over this. So maybe I will calculate f prime of 1 over here. This is 4 plus 1 divided by 1, which is 5. So here's my final answer. It's 1 divided by 5. Like this, inverse function theorem. Next question. We want to determine all points, and by that I mean x values, where the tangent line is horizontal. Horizontal tangent line means it has slope 0. It means the derivative is 0. So let's take the derivative. I will use this dy dx notation. Dy dx. This one is product rule. We have first times the derivative of the second plus the second times the derivative of the first. Now we want to find all x such that f prime of x is 0. So we do this. Okay, let's factor out what's common to both, which is an e to the x and an x to the 4th. We're left with x plus 5. Okay, find all x values such that this is 0. It means one of 3 things. Either e to the x is 0. We know this is never 0. So never 0. E to the x is always positive. Okay, so then we move to the next term. Or x to the 4th is 0. That happens at x equals 0. Or x plus 5 is 0. This happens at x equals negative 5. And so this would be our answer. 0 and negative 5. Wonderful. last question, and this is logarithmic differentiation. Okay, use logarithmic differentiation to find the derivative of this function. And how do we go about this with logarithmic differentiation? Well, first, we take the natural log of both sides. So ln of y will be ln of, we have x to the 8 plus 1 to the 1/2 x power, and then divided by this, I'll go ahead and write this as a power. The square root of x to the 9th power is x to the 9 over 2. So we have x to the 9 divided by 2. Now, we have to use properties of logarithms as much as we possibly can. So the first one, you see a quotient, this will turn into a difference. So we will have ln of, we have x to the 8 plus 1 to the 1/2 x power minus ln of x to the 9 over 2 power. We can take one more step here. You see, we have power inside the log, power inside the log, so we can bring that out in front as a times. So we have 1/2 x, ln of x to the 8th plus 1, and then we have minus 9/2 natural log of x. This is as nice as we can get it, but we have to remember, this was ln y. Maybe I can even copy it every time. I have not differentiated anything. I have just simplified the natural log of this quantity. Now, we're ready to differentiate. The left-hand side is really chain rule, so we have 1 over y times y prime. Now we start differentiating the right-hand side. This part, well, how are we going to differentiate this? First of all, I see one function times another function. So the first thing will be product rule. We have first times derivative of the second. My second function in and of itself is chain rule, and it will go 1 over x to the 8 plus 1 times derivative of the inside function, which is 8x to the 7. Okay, so far I have first, derivative of the second, and then I write plus, we have second, times the derivative of the first, which is just 1/2. This, so far, is the derivative of this, using the product rule, and there is also chain rule there. Now, the derivative of minus 9/2 ln x is minus 9/2 times 1 over x. Okay, my differentiation part is done. The final step, you see we're trying to solve for y prime, so we just multiply through by y. So maybe I will copy y here. Paste, there's y. And then times, we have all of this. Well, maybe I'll write the first term. You see I have 1/2 times an 8, which is a 4. So in my numerator, I have a 4. And x times x to the 7th is x to the 8th. This is not required. You can literally just recopy what you have above without simplifying. But I just took that small step. And then I have plus 1/2 ln of x to the 8 plus 1. And then I have minus 9 over 2x. And this is this derivative. We found this using logarithmic differentiation. So this is the end of sample test 1. Good luck studying for the test with this material and all of the rest of the materials, and good luck on the test. Thank you so much.